velocity. Okay, it follows Newton's law. Summation force equal to 0. Okay, summation force equal to 0. So what we learned last week, actually summation force can be also expressed using vector system. Okay, and that means sum of all force acting on the particle should be 0. Okay, from Newton's second law of motion, force can be expressed by mass times by acceleration. Okay, so summation force also can be expressed by mass times by acceleration. Okay, on the Earth, theoretically, if particle, the mass will not be 0. Okay, the mass will not be 0. So if this equation equal to 0, so that means the acceleration will be 0. Okay, clear? Because only 2 terms. Mass is not 0, so that means acceleration is 0. Okay, based on this condition, the particle is moving in constant velocity or at rest. Okay, a drawing showing with all force acting on it is called a free body diagram. Okay, that means we find a mass or particle, we draw the all force acting on it, and it's called as a free body diagram. Okay, here we have to mention 2 common connections in this subject. One is springs. Okay, the other is cable and pulley. Springs, we will use Hooke's law to analyze its effect. Okay, cable is flexible. So generally, when force applied to cable, there must be tensile force. Okay, because they cannot provide compression. So cable, its effect is tensile. Okay, for a spring system, simple situation, we only consider linear elastic effect. Okay, only linear change. And in practical work, like what we analyze the real situation, like civil engineering, even I believe even in mechanical engineering, spring system can be complicated. They will consider elastic and plastic situation. But here, in fundamental subject, we only consider elastic here. Okay, but in the future, they will include plastic part. Okay, if we consider it's a linear elastic string, that means the change in length is directly proportional to the force acting on it. And elastic, that means spring stiffness is a constant. Okay, generally we use K to express its stiffness. Okay, we use K to express stiffness of spring and elastic situation. So force magnitude force magnitude can be expressed as this equation: spring stiffness times by displacement. Okay, spring is stiffness times by displacement. Displacement you can imagine is a length change. Okay, follow Hooke's law. That's okay, you can keep eating. I understand in the morning most of you are hungry. Okay, clear? Clear? Okay, displacement or length change can be represented using this relationship. That means original length, not original, deformed length minus original length. Okay, deformed length minus original length, which is the change of length. Okay, is displacement. So if this term is positive, so that means F pull on the string, positive here. That means the length of string increase. Okay, if this term is negative, that means we push on the spring, so we make the spring shorter. Okay, that's a spring system based on free body diagram. Okay, then we talk about cable and pulley system. Okay, for simple consideration, we assume the cable weight can be ignored. Okay, the cable weight can be ignored. Simple situation. Okay, and then the second part is they only can support tension. Okay, only tension. Okay, and this force always act in the direction of the cable. So what's the cable direction? And it is also its force direction. Okay, only tension. So here, only tension. Okay, then we will also ignore the friction come from cable connected to the pulley. We will ignore it. So that means there is no friction here. Okay, if no friction, that means the force will not lose. So the force will not lose. That means for this cable, two sides, its magnitude should be the same. Okay, clear? Its magnitude should be the same. No friction, so its magnitude should be the same. Okay, so magnitude is the same. That means the cable is subject to a constant tension. Okay, then smooth contact here. if an object rests on a smooth surface, okay, smooth surface can be from description in a question. Smooth surface, then the surface will exert a force on the object that is normal to the surface. Normal to the surface, this one. Okay, and there is no friction. And then for this system, if we draw free body diagram, it can be expressed like this. We have a cable force, only tension, cable force. And then this pulley has its weight. Okay? Maybe not pulley, maybe it's an object. Okay, then here this surface only provide normal force. Okay, so its free body diagram looks like this. Clear? Okay, when I look at free body diagram, I remember when I was a high school student, I don't understand my physics teacher talk about free body diagram because her drawing is bad. And I feel her description is also not very clear. But when I joined Taiwan Tech as undergraduate student, I feel my teacher to teach free body diagram much better than what I learned from high school. But I didn't say I'm better than your physics teacher. Okay, I'm talking about my experience. Okay, my engineering statics teacher explained this phenomenon much clearer than high school teacher. Okay, procedure for drawing a free body diagram. First of all, I thought we should have one more step from not just from this slide. First of all, we should observe our question clearly. To draw free body diagram, we should observe question clearly. Okay, then we plot the outline of the shape. Okay, we should isolate the particle from its surrounding. Okay, then from our observation, we should show all the force based on our observation. We should indicate all force, and then we should identify which is active force. Okay, set the particle in motion, and what is reactive force. Okay, reactive force we can consider as a constraint or support, tend to prevent motion. Okay, then the final part is we should identify each force, and identify, that means we should include direction and magnitude. Okay, direction and magnitude, if they are non-information, so they are non-force. But if they are unknown, we should use letter or direction. More complicated expression is use vector system to express unknown force. And theoretically, unknown force is, I thought in this subject, is what we should work on. Okay, that's a general procedure for free body diagram. Okay, then here is two examples how we work out free body diagram. Okay, left hand side is a crane lift. Okay, so if our object is this one, is this truck, so we can have its cable. So we can have free body diagram. Cable provide tension. Okay, then this truck has its weight. So gravity load is downward. So theoretically, these two forces must be along a line. Okay, theoretically. Okay, we haven't discussed this content, but they must be aligned. Okay, otherwise that means this trunk is rotating. Okay. Theoretically, they must be aligned. Okay, then right side. There is a weight here. Then we use two cords connected to this object. Okay, for simplified analysis, we didn't properly consider the element effect. Okay, we simplify the question like this. So these two forces can be extended. Okay, then this force, gravity load, which is the weight, also can be extended. So these three forces, this situation we call as a concurrent. So they intersect at a joint. Okay, so that's a simple, simplified free body diagram. Look like this. Okay, here I want to mention theoretically this kind of system. I don't know whether you still remember the physics concept. Theoretically, if you want to find the center of gravity, so you can lift, okay, like cable system, lift this trunk, and then maybe you lift this direction, so you can find a vertical line here, okay, and then you change the other direction, lift again, and then to find the other vertical straight line. So this straight line intersection, which is the center of gravity. Do you remember this concept? No? Okay, only few of you nod your head. Okay, anyway, we change direction to lift this object, and then the intersect line, which is this joint, is center of gravity. Okay, using this. Okay, then this system, I just described a practical problem. Okay, and theoretically, in civil engineering, I don't know about other subject, other department. In civil engineering problem, like whole structure of this building, we have many elements. Okay, like each column, each floor plan. Okay, and we also have lots of beams. To put into numerical software, we use simple element to express this kind of force. So maybe, okay, I use this. Okay, here maybe we have a color. So we just use one element to represent the color. Okay, one element to represent the color. And generally one element, that means in computer, maybe they just have a line and two joints. A line and two joints. In software, to analyze whole structure, they only one element, only two nodes and one line. So that's color. If we have big, okay. So also two joints, one line. Okay, the other color look like this. The reason we simplify the question like this is computer cannot solve too many combinations, too many joints, or too many elements. So we should simplify the question. Okay, but this simplification cannot analyze local value or regional value. So for example, if we have very strong force applied to this element, so probably damage will happen here or here. But if we use simple system, we cannot identify local value. Okay, clear? So that's a practical problem. So if practical case, our focus is local value. So we should use the other approach to only analyze this region. So theoretically, if we only analyze this small part, boundary condition is important. So we have to identify how to give boundary. Okay, and then to properly analyze the real case. Okay, that's for structural application. In my area, I'm geotechnical engineering. You know what's a geotechnical engineering? My research area deal with soil and rock. Okay, civil engineering problem in soil and rock. Okay, but what kind of problem we will face this issue? For example, if we have a tunnel. Okay, tunnel for MRT is relatively simple because the inference range, okay, in terms of its embedded height is about 40 or 50 meters ground surface only. Okay, but if tunnel in mountain, maybe, okay, this distance is 1,000 kilometer, not kilometer, 1,000 meter. 1,000 meter. Okay, 1,000 meter. If our software should analyze this 1,000 meter, you can imagine how many elements and nodes we need. But not necessary. Not necessary. Our focus maybe only this part. Okay? So if that's our concern, boundary condition, we should give reasonable stress. Okay, reasonable stress to analyze this region. Okay, that's why I want to express. So to find some regional problem in numerical software, we should give reasonable boundary condition to simplify the equation. Okay, otherwise, even I give you one supercomputer, you still cannot solve it. Okay, I can tell you. There is a professor. He undertake the research regarding the dynamic problem. That means earthquake problem. So theoretically, earthquake problem require computing time is much more than static problem. So static problem, if we need 1 day or 2 days to analyze, and dynamic problem, earthquake problem, that means we need a month. Okay, a month. So you imagine if you are a student, you press enter button, then you wait for a month. And if your result is wrong, that means this 1 month disappears. Okay. But anyway, real situation is like this. Okay, then we have a look. Example 3.1. The sphere shown here has a mass 6 kilograms and is supported by load system, and draw a free body diagram of the sphere. The core CE, okay, CE is here, and the nut at C here. Okay, then if we look at this mass, we have self-weight. Okay, then we have 2 normal force come from these 2 surfaces. Okay, 2 normal force. Okay, here is 30 degrees. So that means here is also 30 degrees. Okay, because it's normal force. Okay, then we have this code provide tensile force. Okay, provide tensile force, which is here. So free body diagram for this object can be expressed here. Okay, then we know self-weight is 6 kilo. So in general calculation, we will transfer the unit as a consistent situation. So we will convert to Newton. Okay, 6 kilogram times by 9.81 become Newton. Clear? Okay, this term you should remember. Will not pivot. Clear? 9.81. Okay, this term you should remember. Okay, then free body diagram, we also need to analyze the core CE. Okay, CE, which is this one. So CE only has tensile force, because it's straight. So only tensile force acting on it. Okay, for nut C, we have tensile force come from CE. Okay, then we have the other code come from okay, I call it the CB. And this is also code, so also tensile force only. So this one is tensile force, this one is also tensile force. Okay, because both of them are code. Okay, you can consider both of them are cable. Okay, the other is come from spring. Okay, this spring, if we don't know, from our observation, this tensile force is this direction. This CE tensile force is this direction. So table force is here. But if we consider free body diagram for this case, we don't know this, but we know this one is this direction. This one is this direction. So this spring must be this direction. The reason is if we find the horizontal and vertical component, this tensile force will have horizontal this direction and vertical this direction. So horizontal this direction, to cancel it, this spring must be this direction. Can you catch this point? Okay? In order to balance this joint. Clear? Okay? Okay, here we go to coplanar system. For coplanar force system, as I mentioned, this is two-dimensional situation. Okay, so that means all force can we observe they are on the same plane. Okay, it's called as a coplanar. So particle is also on this plane. So most common use plane is XY coordinate, okay, which is a plane. Okay, if the question is two-dimensional problem, so that means we can express using caption vector system. And summation force equal to 0, so that means on caption vector system, x direction and y direction, all this summation also equal to 0. Okay, so using this term, x does not influence y, so that means they are independent. So x should be equal to 0, and also y should be equal to 0. Okay, clear? So, to solve the question, here we have two equations can be used to solve two unknown. Okay, we have two equilibrium equations. We can solve two unknown problems. Okay, this is an example. Consider a free body diagram of the particle subject to two forces. Okay, one is non-force, 10 Newton. Okay, the other is unknown force. Okay, they are along x-axis. Okay, to achieve equilibrium, summation x-axis force should be equal to 0. And we define this direction. That's a general definition. We define right direction as positive. Okay, that's a general definition. It's the same as how we define x and y. So x, that means that direction is positive. So the same, we define toward right as the positive situation. So that means summation horizontal force equal to 0. So horizontal force, okay, here we define F direction is toward right. So that means here is positive toward right. Okay, and 10, we already know it's toward right. Okay, so also positive 10 should be equal to 0. Okay, that means F is negative 10. Okay, when we work out F is negative value, so that means F real direction is opposite to what we assume. Okay, if it is negative, that means the direction is opposite to what we assume. Clear? So for further calculation, theoretically lots of questions you don't need to care. And unknown force, which direction you assume. Because for final calculation, if you found your answer is negative, just opposite direction. Okay? Clear? Okay, so here. So positive, that means toward right. Opposite, negative part, that means is opposite direction. So to achieve equilibrium, this force toward left. So we probably finish this question. Example 3.2. Determine the tension in cable BA and BC. So BA is here, BC is here. And these two cables support the cylinder with a weight of 60 kilograms. So remember, for general calculation, we will transfer unit become Newton. So here, show you what's how to make 6 kilogram become Newton. Okay? Okay, then we know this information self-weight. So that means this cable also provide tensile force. Tensile force. So that means this direction in order to cancel self-weight. So cable provide a force this direction. And here, I just reveal some content will be taught behind. If tensile force, we generally use the term lift away the joint. Okay? So that means for this element, the joint is here. Lift away the joint. So it's tensile force. So that means to the other joint is here. And this cable also tensile force. So that means tensile force is also lift away the joint. Clear? Lift away. Tensile force lift away the joint. Okay? So the same, these two, they are also cable. So you can see lift away the joint because cable only can provide tensile force. Okay? And these two forces, we already have an angle. We can work out its vertical and horizontal component. So theoretically, for this joint, horizontal component and vertical component should achieve equilibrium. So that means both of them should be equal to 0. And from the definition, toward right is positive. and upward is positive. Okay, then we already know the force direction. So we can work out its component. For TC, cosine 45 degrees. So that means toward right. So it's positive. And for TA, follow this ratio, but it's toward left. So it's minus, negative. Okay? So it should achieve 0. Then for vertical component, TC sine 45 degrees, upward, so positive. TA follow this ratio, also positive, because both of them are upward. And then self-weight, not self-weight, tensile force come from this cable, so negative, because it is downward. Okay, should achieve equilibrium. So two equilibrium equations can help us solve two unknown. Two unknown is TC and TA. So follow this equation, we can solve TA equal to this roughly 0.8839. Okay, TC. So put TA, not put TA, replace TA by this value. So we can work out TC first. Okay, then we know TC, we can work out TA. Clear? Clear? Okay, as I mentioned, leave away force. Tensile force is leave away force. Cable is tensile force. So we can go back to check previous equation. So you can see cable leave away the joint. Okay? Because they are tensile. Clear? Any problem for today's content? Okay, if not, we finish class here. Thank you.